So last time we finished with ideal fluids and we started viscous fluids, right? That was the last part of the last lecture. We continue from there. Ideal fluids and viscous fluids. What is the difference?
Different boundary layers don't interact with each other. Different layers.
Boundary layers?
Sorry, not boundary layers, just layers. You have nothing that.
More general, yes, okay.
With
What's the picture of an ideal fluid? Ideal fluid does not dissipate its energy when there is no external factor working on it. Propagating, it will keep on propagating. And non-ideal fluids have dissipations, different types of dissipations. What are different types of dissipations?
You have a dissipation that is just, I guess, loss of momentum, like forward. Like I move forward.
Things can move forward, but that's not the loss of momentum.
No, I'm talking about something that you lose momentum in the direction you're going and you lose momentum in other directions that you're not going, which is sort of like getting dragged along.
When we talk about dissipation, it means dissipation of energy. Same for momentum as well. But any fluid or any object which is moving, its energy can change only if there is an external factor. However, if there is internal dissipation for the system, its energy can dissipate as well. So when we talk about fluids, what kind of dissipations you are familiar with? One is, of course, we talk about viscosity and
Turbulence.
turbulence. Turbulence is a kind of non-linear viscosity, which we'll talk about. Also some kind of convection and because of thermal conductivity, sometimes thermal heat is produced. Okay? So these are the factors through which a fluid can behave in a non-ideal manner, which we can call real fluids. Every fluid is non-ideal in principle.
You have also dissipation that relates to boundary conditions. I talked about it with like if you're like in a box, if it's not like an infinite fluid, then
So,
you have curl being formed at the edges, and then something is not that.
okay, so these are two layers. Okay, a fluid is propagating between the layers. What if the fluid is ideal? You mean to say that it will form some curls here, right?
Yeah, because you have something pushing the top of the. You have a spinner that pushing the water is pushing the top of it.
Only if there's a friction between the lowermost layer and the solid. When we say ideal fluid, we can also think of ideal layer, right? Non-frictionless surface. So when an ideal fluid moves, it does not interact. When it does not interact with the surface, this is an idealistic picture. It can propagate without dissipating any energy at the boundary. So just because of the boundary, you do not necessarily lose energy. You lose energy when the system is real. System is real means two factors. One, fluid is real, non-ideal. Second, surface is a friction, which is the realistic situation. Okay. Now I want you to picture equation of continuity. How will it change for an ideal fluid and non-ideal?
If you have non-ideal
Continuity means fluid is moving, you have volume, amount of mass which is lost by the volume is same as flux and these two are equal, basically flux integrated dot df. When the mass lost is equal to the mass leaving from outside, this is what you will continue the equation. How will it behave? And we can write the equation as well. how will this equation behave when the fluid is non-ideal?
I don't think it will change.
It will not change. Continuity is continuity. It can change only if there is some factor that produces particles or mass. So the continuity equation remains the same. However, the momentum conservation equation that changes. Okay, this is one of the ways we write Euler equation. What is pi ik here? Momentum flux tensor. What this equation shows? This shows the rate of change of momentum, the same as the flux of the momentum propagating along x coordinate. Okay.
So the flux controls the rate of change of momentum.
Yes. And we saw that the nature of pi ik is something like that. So when I say del pi over del xk, what it means? The flux of the momentum in the fluid is allowed only through two channels. There are only two ways momentum flux can propagate. One, of course, pressure. Okay. Second, bulk motion. These are the bulk motion terms. If the fluid is moving, when I'm talking, air is coming out, that's the bulk motion, not the random motion of the particles. So the momentum can transfer only through bulk motion and pressure. There is no third way in ideal fluid. However, now we talk about real fluids where the momentum can dissipate between the fluid itself. So the picture is like this. There are two layers. Can you imagine an ideal fluid? How an ideal fluid would look like?
Can you repeat?
Can you imagine microscopically what goes on inside an ideal fluid?
Vibrations. Just vibrations of
Vibration.
microscope.
There is no vibration in the fluid
I mean,
in general. Yeah. It's the random motion of particles.
yeah, that's what I.
Particles are randomly moving. So whenever the particles are randomly moving, it's just an idealistic picture to assume that there are two layers which can propagate without affecting each other. In general, it cannot happen. So ideal fluid is technically unphysical, but it still works when the fluid's behavior is close to the ideal nature.
So for ideal fluids, we can have a flow that is 0 meters per second for the bottom layer and 10 meters per second for the top layer. It's actually discontinuous, and it will just stay like that in steady state. There won't be any process of mixing.
There will not be interaction between the layers.
Okay.
Okay, because layers do not affect each other. But there is a problem in that concept itself. In an ideal fluid, the motion takes place because of the bulk properties like pressure gradient. If you put up a pressure gradient, whole fluid will behave in a similar manner. So for your setup, you have to put up the pressure gradient in certain manner that it automatically has this kind of gradient. Okay. If you do not grade this kind of gradient, it doesn't exist. It will remain to be the same. So when the particles are moving randomly, they are changing the location between layers. So necessarily in every fluid, the layers affect each other. But still there can be situations where the fluid can be considered ideal. It's very close to ideal. When interaction between the layers does not cause loss of the energy, or the loss is negligible. For example, a very hot gas, 10 years case, density is very high. So if it's moving, you necessarily do not get that particles do not interact that much with each other, so there is no transfer of momentum between the layers from both. So it's basically it's close to ideal case. In general case, whenever you are to more realistic you are, there will always be an interaction between layers. Thus, the energy will be lost and the momentum will transfer. So, the transfer of momentum for the coordinates is allowed in ideal fluid only through two channels: bulk and pressure. But now we introduce realistic terms where the momentum can transfer between the layers. So, we define realistic momentum flux. Sigma I can apply. Now we have to find out what is the nature of this sigma term. This term shows the nature of the fluid with which it can transfer its momentum between the layers. This whole stress can be represented as sigma k, which is so this sigma ik, this is total stress energy stress tensor. And this is viscous stress tensor. Why is it a tensor? Anyway, this is a tensor. Momentum has tensorial nature to flow because
each coordinate is its own scalar, and then each coordinate needs a vector to describe itself.
we discussed a lot about the physical nature of pi ik. It's the flow of momentum in one direction across I with a constant gray surface, and both can be different. Okay. Now we need to find out the physical nature of this sigma ik prime. Viscous stress tensor. This is total stress tensor because of pressure plus the viscous term. This is only viscous stress tensor, which is coming because of the non-ideal nature of the fluid. Okay. So now we define this stress tensor. As I already said, sigma is primarily due to the interaction between different layers of fluids, relative coordinates. So it has to be made by the velocity of different components in different coordinates. So it has to be coordinate derivatives of these velocities. The two types of viscosity is introduced here, eta and xi. If you look at these terms inside bracket, it is made of the derivative of velocities with different coordinates, del vi or del xk, and it has three terms for all I, all k, and there are two terms here for velocities. Somebody asked in last lecture, why do we need two terms? I could not answer because I didn't know at that time, but we'll talk about it. And we have similar terms here, which show what does it mean when you talk about del VL or del X. Yeah. This is basically divergence of V.
So that is an important.
dV over dx, dvx over dx plus dvy over dy plus dvz over dz. There. Similar terms. So what it means is it just subtracts the similar terms. So we have only shear terms here. Why do we have 2 by 3rd factorial? One comes from here, which is similar. One comes from here too. And del ik in 3-dimensional is equal to 3. Because in one dimension, it's 3 dimensional. Del ik, del xx plus del yy plus del zz. This is also 2, so you have to add all of them. In that case, it is 3. So basically, 3 factor comes from here. It just cancels. Because there are 2 terms, so you get 2 here. So this is how you just cancel the similar terms.
Wait, but why? If you have, just look at one specific I and one specific k, and I equals k, then you have the vi over d. It's like the first 2 terms give you twice this amount. Vi over xi and vi over xi. Then minus 2/3, del ik should be 1. No? Why is it chronicle delta?
It's 3-dimensional chronicle delta. 3i and 3k. So del xx, del yy, del zz.
No, I can k out the indexes. You only have 1, 2, or 3. It's a
And the dlxx, that gives del xx, one term. In a yy is another term. Then you have zz, there is another term. So there are 3 terms here, there are 3 terms there. All together you take to cancel all the terms. You have to take each and everything twice or thrice. This is why in 3 dimension this connected delta will be. You can do the same thing in 2 dimension as well.
Yeah, okay.
You will need only 2 terms in that case.
Couldn't you write something like that only affects the coordinate ik? Couldn't you say something like, I don't know?
Yes, 2 dimensional. You mean 2 dimensional?
No, just say minus 2 del ik dou vi minus over dou xi. What you get is that it cancels out. You just want to cancel out on the diagonal, right?
Say it again?
You want to cancel out the stuff on the diagonal.
Yes,
So-
only the similar terms.
Why not just write minus 2 del ik and then one of the things from there? Or why not put del ik over the entire expression? Because it will be doing the same. You have these.
It's just a matter of representation.
Okay.
You can write it in all manner. You can define del in certain manner that if you write
I understand. Yeah.
if
Each
you
one of
open
them gives you.
2, yeah. So for xx or yy, z, you have 3 terms. This is why you cancel 3. And because there are 2 terms, this I will get 2 here.
Okay.
Now, why do you need 2? Somebody asked last time. Why don't you just work with 1? Del vi or del xk. It's like when you talk about del y, which means the change of velocity of x coordinate along y coordinate. Okay. To maintain the homogeneity of the system, fluid at a particular point has same properties on all sides. So when you talk about one gradient, at the same time you have to talk about the other gradient in the same coordinate as well. If you don't do that in certain cases, it will create asymmetry in the fluid. So to have the coordinates symmetry, you have to define two terms. But you do not always need this. The reason is we will solve some of the problems, and the system is one-dimensional. One term will be enough. But that depends on the problem. This is very general version of this. Okay. So the terms inside the bracket only show the derivative of velocity with respect to relative coordinates. Can you hear me? Okay. All right. So these are basically shear terms. Shear means between different layers. So eta is simply shear viscosity. If the fluid is viscous, the viscosity will be along the same coordinates as well. If there are two adjacent layers, they cause dissipation from one to another because of the shear among them. We call this shear viscosity. But if the fluid is general, it can have viscosity along the line as well. Nobody stops it. Particles are having interactions everywhere. So dissipation can be all directions. So this is why I introduced one more term which has similar terms. It's divergence. This term is basically divergence of V. What does divergence mean? Basically what it means.
The rate velocity is created. The rate velocity is created in the volume or something. If you have a volume and some velocity is going in, some quantity is going in and more quantity is coming out, the divergence will be positive. Why? If you have the divergence of mass, it's just how much mass is being spontaneously created.
How much mass is?
Being created spontaneously.
Not created. Net mass that comes in and
yeah.
It just means any physical quantity. Its divergence means it is diverging in space. If you inflate a balloon,
oh yeah, I'm thinking one in space.
You are thinking else. If you inflate a balloon inflates. Simply means the fluid inside the balloon has a non-zero divergence. Suppose you fill the balloon with water and you blow water, will it inflate? It will not. Because water is incompressible, its divergence is zero. Its velocity does not diverge. So divergence means either expanding or contracting for other terms. So this term shows either expansion of the fluid or compression of the fluid. This term shows the interaction between different layers, so shear, and this is bulk viscosity.
if the dissipation is only in this direction, yeah. So what terms will be left? Or
We will take care of, we will see the examples where water is flowing in a pipe. In that case, if the water is, we will see the examples, we will solve the problems. If water is flowing in a pipe, the shear will be along Y. If it's water, these terms will anyway be zero. But then, suppose this is the pipe, air is flowing like that, so your shear will be along Y because of the friction with pipe. But once the air comes out, it expands, then the other terms will also come into picture. Now here, Okay, so we know these terms. These are just the coordinate derivatives of velocities. What is the nature of eta and xi?
These are just parameters for the fluid. Right?
Parameters for the fluid. Can it depend on? So parameters of the fluid has two things. Either it is same for the fluid, like water in this bottle, water outside in the tank. Is it same for all of the waters, all types of waters, or it is different for different types of water depending upon their parameters like temperature, density. Density is same for water, but temperature can be different. So what parameters theta and xi should depend upon? Universal properties of the fluids, same for water, different for honey, or it should be different for same types of fluid given different parameters.
You gave the example of air in a balloon, and when you add pressure, when you add more air, you add pressure, and pressure causes it to expand. That's the excited. So what if there's a situation where you have enough pressure and it stops expanding, and then the excite has to depend on the pressure?
So that is taken care of by damages.
Okay.
So here we assume, we make an assumption. This is an empirical expression.
Okay. Oh.
It cannot be derived. Now if somebody asks me why there is no square term here, why don't you consider square? I don't know. Okay. This is empirical term which works. I'm not aware if there is some standard derivation of this term. But it takes care of all our intuition, how the shear should take place, how the expansion and contraction should take place, so it is reasonably okay. Now we assume that this eta actually depends upon the fluid properties, but then we define kinematic viscosity, which is eta over rho. Anyway, but here we can consider this as constant. It does not depend on coordinates, because fluid has same physical nature at all coordinates. So eta and xi are coordinate independent. That's our assumption. We'll go with that.
Independent of coordinates.
Independent of coordinates.
What about variables like pressure or density?
It can change with the I'll tell you. This is, for example, this viscosity, which is the ratio of the kinematic, the shear viscosity and the density. This is assumed to be constant. For water, it is incompressible fluids. Anyway, density always remains same. But if it is not incompressible, in that case, this is assumed to be constant, but this ratio keeps on changing. So it is assumed that eta is independent of fluid parameters. However, it is not necessarily true. It may change. I'm not aware in which conditions it can change. But we will go with the assumption that eta and xi are universal parameters assigned for
This situation was set.
for the fluids. Okay. So it should be clear. If there are questions, ask me.
I have a question.
Yes.
You said that in the example of a very hot gas, and it's very close to ideal. Doesn't that mean that the parameters here should change by the temperature?
Which parameters?
A times I.
So that's what I said. In general, these viscosities should depend upon the fluid parameters. We did some experiments in first degree, etc. You may have done. How do you find the viscosities for different temperatures and different? So it should change in general. But at least these are independent of the coordinates. Given. So we'll go with this assumption, but we'll have more comment on that. I will try to find out what is the exact nature with the fluid properties. So when you do these experiments with the Stokes law, you put up this small ball in the glycerin, you try to find out the viscosity of glycerin. You basically find out the universal viscosity of the glycerin. So if you change the temperature, unless you change it a lot, you still keep on finding the same value. But it may change it after a certain threshold. So now we derive Euler's equation for viscous fluids. Now, when we derive Euler's equation, we consider ideal fluids. Euler's equation means equation of motion for ideal fluid. When we derive the equations of motion for viscous fluids, we call them Navier-Stokes equation. See that? Okay. What's Euler equation? Okay, we are familiar with this. So you can check the density on the other side, but we keep it here. And we wrote this in tensorial form. This is for ideal fluid. For real fluids, you add extra term. Sigma k prime. You can consider sigma prime, which is total stress tensor, but you can see it encompasses both the terms. Sigma was sigma ik prime plus pressure. Now we have this nature of sigma ik prime. You put it there and estimate this.
Sigma tab because the shouldn't the sign of sigma of the sigma dot x should be the same sign of dot p dot x?
Say it again.
Shouldn't the minus be dot p dot xj and then minus dot sigma dot xj because you're adding it?
No.
In the momentum tensor, it's just added. So if you're adding one, you should add the other.
This is the way it is defined. It should automatically come how the dissipation takes place.
Yeah, but here we're just doing something for p, and then where you want to do the same thing for sigma. So here we have minus p, so we should have minus sigma. It's the same.
It's minus gradient of p.
So gradient.
It's not minus p. It has the term.
Then okay, so it should be minus gradient.
It's not just. This is the gradient.
Yeah. Okay. So
Can you explain?
I think there's a sign here. Even there should be minus sign, right?
because you should be treating them the same. You're just pressing one here.
But I wrote this pi I here. What did I write?
Rho vi dk.
Okay, first let's write rho first. dk plus p then ik and then
Plus sigma.
oh it was minus.
Minus.
It was minus. Change the sign. If I did I write plus there?
It says minus.
Did I write plus or minus when I wrote?
It says minus. It says plus. Sorry.
No, put minus there. Okay. Just change the sign in the first expression that I wrote. You're right. Now it's plus here. Okay. Plus. Okay. Now this is double derivative. Del of del xk, del xi. I can switch the derivative. I can take the derivative with I first and then k later. So I will write only this part, not the left hand side. Okay. This is same up to this plus eta. This is basically del square v, it's Laplace, but we'll change it later. Now I'm changing the sign here. is ik. I can contract ik with k, so it becomes del or del xi. Do the same thing here. Now look at three terms. This, this, and this. This portion is same in all the terms. Do you see the similarity? Are they same? This, and this. What's the difference? K, L, and L. The same or different?
They're different values. You have K and L. I don't understand.
You take some over K and L.
What it means? Okay. That means everything is not clear.
Yeah,
Del V or del XL. What it means?
Some.
sum
I
over
think
fi, yeah, sum over all of them.
Del Vx over del x plus del Vy over del V.
Divergence.
Let's write it, okay?
Yeah,
Del
okay,
Vx
divergence.
over del x plus del Vy del y plus del Vz z. Okay? This is del Vk over del k. So if it is k instead of L, will it change? Will the right hand side change? It doesn't matter. Okay? So when you have two contracting indices, this is same. It had del Vp or del Xp, it doesn't matter.
So why?
Did you understand?
Yeah, but so why you write it as three different letters? It means the same.
We started with dVL or dXL, del VL. It was just a contracting variable, so we gave it a separate variable when we defined the common sigma. Okay? But even in that case, when I wrote this term, it was pretty common. I just wanted to keep this as a separate variable from these two. But that does not matter, it's always divergence. This is divergence of V. Divergence of V is always divergence of V. Just so these three terms are similar. Okay? Should be very clear. So if these are similar, this is one, this is one, this is one, then I can take them out.
Oh, so just not to accidentally add them up. If if you wrote here L instead of K, so I would think, oh, maybe I can just add them up. Like
You can add them. Now you can add them up. Now you can add them up.
Oh, so I can.
But if instead of I you have K here, then you cannot add them. This I and K are different.
Yeah.
Okay?
Wait, but so why do you have over at the first thing on the left one more? Why is it K and K if you're doing the XI?
No, I'm not doing Xi. I'm always doing Xk. You're missing some points here. Okay, so we started from there.
Yeah,
This is del or del Xk.
yeah.
And I did exactly the same thing. You can see the first term, del Vi del Xk, del Vi del Xk del Xk. Okay?
Yeah.
Second term, del Xk.
Okay.
Here is also the del Xk, everywhere it is del Xk. But then I contracted this with this. Okay, so I also wrote this directly. What I did is del Ik, del or del Xk, it can be written as just contracted this way. Because del Ik means I is equal to K.
Yeah.
When I is equal to K, you can write as I. So I use these identities. Now everything is I here. And these divergences are always same. So these are same values. So I can add them up. Eta. And what is this?
The plus symbol.
Yes.
Plus.
This is del square V. Okay. So let's start it down. del square VR plus eta. Eta comes inside. So I'm taking it inside. Let's take it inside. This is eta. This is eta. This is eta. And I take this common. Eta minus 2 by 3rd eta is 1 by 3rd eta. 1 minus 2 by 3rd is 1/3 eta plus xi. Okay, now it is simpler expression. I can write the other terms here, which I did not write before. Okay, now it's full equation from here to here. It can be written in vector form as well. Here, let's write it here. How to write this in vector form? Yes.
I just wanted to ask a question. Why can we rewrite that dou p to the xk as dou p to the xy? I? No.
Which one? Which term you mean?
Dou p to xk.
Yes.
Yeah. Can we
This is
write-
di. No, this is not dp. This is.
But does it matter?
It does matter
Why does it matter?
because of an equation. You see this term here. What we are finding out. Let's write this term. Okay, separately. What was this term? Rho dvi over dt. Remember this. This is total differential. You should always remember this. Del vi over del t. It was del vi over del t plus v dot grad vi. Okay? This is v dot grad. Now this is complete. So this is left hand side. Rho del vi del t. So your I has three values, I, j and k. Right? Okay? So when I write this del vi del t, that means left hand side is equation of motion in I direction. So I is specifically denoted here. Then you cannot write ik here. If dvi, suppose I is x, dvx over dt means you are finding the acceleration of the fluid above along x-axis. Then the derivative of the pressure has to be along x-axis as well. This symmetry is not broken. Why? Because One, pressure is isotropic. Second, the fluid was ideal until the here. Then the other terms come into it. So you cannot write del xk here. When I wrote del xk, it was a mistake. Okay? You understood?
Aren't we summing it anyway? So
No.
Eyes one.
that's a vector.
Okay. When you write this, for a certain I, left hand side is I equals x. In one equation, you have only x here, del p del x. When you solve a vector equation has three components. Right? This whole equation has three components, left hand side. These are basically a set of three equations. When you are concentrating along x-axis, so dvx over dt, then your pressure gradient has to be along x. There is no summation there. There is no summation. Summation is only for these terms. When you have contracting terms like that, you have summation. In del ik, you have contracting terms. K, k. I, j, j, k, k. Otherwise, when you have I, this I cannot be changed. Is it clear?
Yes.
Okay. I assume that you studied this. How many of you are in the course of general relativity?
Not yet.
It's a third year course or second year.
Okay. But you studied these things. Where?
I didn't formally learn general relativity.
Not general relativity. This is just
I know this.
mathematics.
Yeah.
Okay. He knows more than me. Okay. All right.
It's like we aren't summing on I because this is a formula for the ith derivative.
Yes, we are not. There is no sum for I.
I
There is sum
is
for.
the thing that's the index into the vector. Like we have x coordinate, y coordinate, z coordinate.
Yes.
That's I.
So
The
when I
other
write,
things we sum.
so when I write just when
Yeah, okay,
some
okay.
term has only one in the index like I,
Okay.
it is only one. Suppose it is
Yeah.
then xi. Now it is summation. It means you have to add all. There will be one vx, x, vy.
Wait,
Okay.
what did you change?
I just changed this just to show. If I had this, then vi del xi, like this. The moment you write this means that all the terms are to be taken.
Okay. Why aren't all the 9 terms should be taken if you do
There are
VI
9 terms,
over
there are just
del
3. There are no 9 terms here.
But if you do vi over xk like before, you have 9.
No.
You have I can be x, y, z, and k can
dy
be x, y, z.
dxk, you have
Yeah, no.
gradient. This is gradient. There
Okay.
are 9. This is gradient of.
So sometimes
But
you keep
previously it was time. It was. This is why you have just 1. Time is 1. Right?
So we just have to remember that there's one coordinate that represents the direction we're doing the math for. Okay.
If there is just one index in these expressions, you mean we are talking about single coordinate. The moment you get contracting indices, you have to sum them. So here, x, y, z all come in one equation. Even if you are solving the equation for x coordinate, you have to take care of all the terms here. This is why you had del equal 3, del I, j, j, k, k.
Some.
This is why you can see. Clear? Okay. When you ask questions, things become clear. Otherwise, I assume that you already understood. So this was a mistake from us. No, it is okay. Where were we?
Last year.
Yeah. What is this? This is divergence of V.
That's the
Yeah,
derivative of
del-
that
yeah.
divergence.
This is derivative of x, coordinate derivative. Okay.
So if I is the coordinate we're summing, if I is the vector thing, then this should be the gradient of the derivative.
Yeah, this is gradient, this is divergence.
The gradient of divergence.
Gradient, divergence of V. There is a reason why we wrote it in a specific manner. Now the equation looks simpler. It's small, it was much bigger previously. Now let's try to understand this equation. If we remove last 2 terms, we recovered the Euler equation. There is a term for this. to write the name, but it is called Navier-Stokes equation. Navier-Stokes equations are the Euler equations for viscous fluids. So if eta is equal to 0, xi equal to 0, these two terms vanish, and you get the Euler equation for ideal. That means fluid is ideal. Now, the moment you have viscosity, you have three extra terms. How do these terms behave? Let's write another simpler version of this. Incompressible fluids. What will change in this for incompressible fluids?
Rho is constant. So anything you have derivative of rho is weird.
Rho is constant.
Rho.
Rho is constant. Rho will remain constant. Okay.
What else?
What else?
The mass is
Huh?
the asymptote is not a constant in a compressible.
Yeah, it is. What is not constant?
The mass in a volume element.
Mass in a volume element is strictly constant for incompressible. Okay, you are talking about compressible fluids. Yes.
Last term.
That is density is constant. Last term.
The
Last term, what will happen?
divergence with the velocity.
You should always remember, if you are sleeping at night and somebody comes and asks you what happens in compressible fluids, you should immediately say divergence of V is 0. Okay? Without waking up, you should say it.
Does that come from like the continuity equation or comes from somewhere?
It came from continuity equation. Remember?
Yes.
We have
The rho T, okay.
densities
Incompressible fluids.
for incompressible fluids. There is no divergence of V.
Yeah.
It should be the V dot grad V is 0, right? Because that's the thing we have d rho over dt, which is 0 plus that equals.
This is 0. Divergence of V is 0.
Yeah.
We derived it several times. We can do it again. This is continuity equation. Open this. Okay. I just opened it. For incompressible fluids,
So gradient rho goes away, rho over
this
dt goes away.
density does not change with time. Density doesn't change with space. So I'm left with only this term. Rho divergence of V equals 0. Rho goes up, so divergence of V equals 0. This is the outcome of continuity equation. Okay. Divergence does not survive. This is why if you fill, I said in the beginning, if you fill a balloon with water and blow, no matter how much you blow, you try it at home. It will not blow because velocity does not diverge. It cannot expand. Yes. So velocity cannot diverge and water cannot expand. These are identical things. So this is a mathematical way of saying that fluid is incompressible, even if there is no density in the terminal. Okay. So for incompressible fluids, how this equation will turn out to be? This will be 0. For incompressible fluids. So our equation is even simpler. But is viscosity 0 for incompressible fluids?
No. No. I mean. No. Yeah.
Water is viscous. So this is why you have this term. Okay. Eta survives. But as I told before, if the fluid is incompressible, xi is anyway 0.
What is the Laplacian term mean?
Huh?
What is there an intuition for the Laplacian term?
Yes, we'll go into very much detail of that when we take the example. So for incompressible fluids, not only this is 0, this is also 0.
It doesn't matter.
It doesn't matter physically. But the second thing is, suppose the fluid is compressible. It not only had this term, but also this term. So the divergence of V couples with eta as well. So even if mathematically you put psi equals 0 for compressible fluid, shear viscosity will also couple with the divergence term. So it's a complicated behavior. But for incompressible fluid, it is simple. Okay, next. Yes. And how this sigma behaves for incompressible fluids. Sigma prime. This was eta. This time is anyway 0. Start to complete this. How will this look like for an incompressible fluid? Tell me all the things that will go to 0.
VL over dou XL goes away. That's divergence.
Ravi,
Anything that has to do with the divergence of V goes away. The VL over dou XL.
tell me where are divergences?
The third element.
Hmm?
The VL over dou XL goes away.
This is divergence.
Yeah.
This is 0. This is divergence of 0.
Same thing on the one next to it. Yeah.
This is also 0. As I said, because they are contracting terms, so you have to take all of them into account. X, Y, and Z. This is why it is divergence. Now these two terms are 0, so our viscous stress tensor simply becomes this for water. Water, this equation can be written as, water means incompressible fluids. Water is just one of them. This eta by rho is called kinematic viscosity. And it is denoted as nu. Just it is scale with density.
This is a non-linear equation.
Huh?
This is a non-linear equation.
Which one? Yes.
Because
Highly non-linear. Your del square term there.
yeah. Wait. No. Del squared can be Laplacian, right? We have Laplacian in linear equations.
There is no v square, right? It's not non-linear.
It's this term makes it non-linear. Non-linear.
There is no v square, so it's not non-linear, but it still does not have solutions. In some cases, solutions can be obtained, but it still cannot be solved analytically. When you take all the terms into account, no analytical solutions to the equation.
Is there not numerical solution?
Numerically, everything can be solved. Now, as I said that when you consider a viscous fluid, the momentum is transferred between layers. So what will happen if the momentum is transferred between these layers of the fluid? How will it affect the energetics of the system? So we have seen that the continuity equation doesn't change, it is same, even if the fluid is viscous. But the momentum equation does change. It becomes Navier-Stokes equation. What about energy?
Does energy diffuse as well? Like momentum does? Between layers?
Let's find the answer intuitively. Forget about maths. Consider an ideal fluid. Take a pipe or tube, glass tube, which has frictionless surface, and you through a piston you push this ideal fluid. What will happen?
Can you repeat?
You have ideal fluid in a glass tube. And a glass tube has infinite glass tube, infinite. And there is ideal fluid here, glass filled with that, and there is a piston, you pushed it. So it gave it some momentum. What will happen? Just from your experience. You don't have experience with ideal fluid anyway. But now, when you consider, just from your experience, let's say any fluid you consider. If you push it, what will happen to the fluid?
Is it incompressible? Is it
It
incompressible?
can be anything, but think about incompressible fluid because you have experience with incompressible.
It's incompressible, then the entire column has to move. Kind of like
Okay.
hydraulics.
Okay, then where it will go? Haifa? When it is moving this direction?
Yeah.
No. Real fluids. Does it happen? If you have a pipe, you push it, it will go indefinitely, it doesn't.
Wait, will not move? Wait.
It will move. How long it will go? It's an infinite pipe.
Oh,
If it's incompressible, there's
Yeah.
nowhere for the momentum to stop. It has to keep moving, it has to be infinite.
Okay. So you are saying that if you have a pipe from here to Haifa and you push a little bit,
If it's incompressible, then
it is incompressible.
yeah, the
Ideal.
What will be ideal fluid? Not ideal. Real fluids. I'm asking about your experience.
No, there is friction.
No, it has to be. If you look at the volume of the fluid from here to Haifa, it's like pi r square times the distance, and that's the volume of the fluid. And if you make the volume smaller here, because density can't rise, the volume can change. So it has to move there.
We found that out the Bernoulli theorem for ideal fluids.
I'm still talking about the incompressible fluid.
Incompressible fluid is not ideal.
So yeah, if it is compressible, then you can have pressure increase instead of velocity.
What we discussed is when there is a friction between the layers, forget about that. In your experience, it will not go, it will stop. After a certain distance, it has to stop.
Yeah.
Why? Why it slows down? Something is taking its energy. You gave it some energy, but energy is going somewhere.
Turbulence?
There is no turbulence. There can be, but we are not talking about turbulence. Turbulence is the next section.
Okay.
Temperature. G means heat.
So bulk volume.
Where the heat is coming from?
Resistance, air resistance. Air resistance.
Air? Forget about it. Suppose there is no air.
Maybe between the particles,
Between the layers.
the layers.
That means whatever we are in viscous regime, so because the friction between various layers, the momentum is exchanged. Now we will see in next section that because of this exchange of momentum, the fluid loses its energy. And energy goes in heat.
So like bulk motion becomes tiny motion.
Bulk motion slows down and all kinetic energy converts into
Okay.
heat. So the fluid here, hotter, you may not see the changes right away, but energy dissipates. If it's an ideal fluid, frictionless surfaces, then you're right. There's no way anybody can stop it. If the world was like that, you would not need motor to push the water continuously. You need water pump. You have to pump it constantly because The world is made of non-ideal real fluids. So now we'll find out how the energy changes in a real fluid. We'll consider incompressible fluids for simplicity. Our purpose is to understand how this extra term that we introduced, it causes the dissipation of energy. Mathematically. Physically we know it does not indefinitely flow. Now we'll consider about only kinetic energy. It's Ek, which is kinetic energy per unit volume. In fluids, we always work in terms of per unit volume. So if you, at a given time, if the fluid has energy Ek, it is propagating, how its energy will change. So our purpose is to find out del over dt.
Wait, but shouldn't it be plus rho epsilon?
Yes, but now we're talking about only kinetic energy. So the problem is, our problem is to find out if there is a kinetic energy. You have to include that. The reason is, when I said it converts into heat, what is heat? Heat is temperature. In enthalpy you have term P by rho, that is technically temperature for ideal gases, but it represents temperature. So it converts into heat. But here our purpose is to find out what is the rate of change of kinetic energy, how it changes. Okay? I can write it like this. Okay? Is a sentence. So now we have to find out this. What is this term? This is precisely what we derived. Take care of all the terms here, only this term. We don't take care of this term because the fluid is incompressible in our case. We will try to see how this kinetic energy changes. Now we have this rho Vi from there. What is del Vi del T?
Minus square root of E plus eta plus
minus, let's keep it plus here. We keep it general at the moment. We have rho here. we are solving for this. We have this here. So I take this rho inside, rho. So rho Vi transferring this term to the right hand side. Minus. Okay? Multiplied with Vi. So this is simply rho Vi. You see, now it is summation. The moment two terms come like that, you have to sum it over all. Not with I. Just wrote it in vector form, but kept last term to be the same. Okay. Last term is, okay, let's write it like this. Del sigma ik. What? So this can be written like this. One term is similar, so we just replace Vi del sigma ik by del xk. minus we'll replace the last thing here. Did you understand? It's just a product. Just open it to form, and then I brought this term in this form. Okay? Fluid is incompressible, so the density can go inside gradient. Doesn't matter. I have written these two terms in this form. We'll just see how it came. If I open this first term, divergence of this is scalar and this is vector. So divergence of V plus here. Let's see this. The thing is, when you open this term anyway go to 0, divergence of V. And the second term is V dot grad of this part. So
Well,
you open this.
That really looks like grad dot grad. The way to make the V vector look like less like grad. The V vector really looks like just grad. Thanks.
Okay. So there is some confusion here anyway, but so when you open this term, V dot grad, it has to be similar to these two terms. V dot. This is the first term. Okay. And the second term is V dot grad P. If you look at these two terms, it is just this term, okay? I'm just adding this. So the first term and the second term, they are basically these two terms.
Doesn't the first term have an identity? Doesn't the first term have this identity that reduces it to half base squared or something?
First term means this.
Yeah.
We'll talk about that. First of all, why I wrote this in this form, divergence form.
Okay.
So these are two terms, okay? These are basically the same term, and this is anyway 0. When you combine that, you get it like this. Okay? So basically, this term is same as these two terms. There's a reason why we write in terms of divergence, because divergence is a flow of a quantity. Okay, is it clear?
Sure.
I define this divergence of this term. Open this. First term is anyway 0.
Wait, so you want to find the flux vector of...
Yeah, how the kinetic energy is the flux of kinetic energy.
Okay.
Okay, so that's the motivation.
Yeah.
So when you define this term, this is 0, and this is basically the same thing. So I can combine these two terms in this form. That's the motivation. Okay. So I can write full equation now. And that's all. Minus. Okay. What is this term?
Which? It's dou xk.
This is divergence, right? Because x is the k is quantity.
So we're summing the divergence of V.
If sigma is
The divergence on the k index, not on the index.
divergence is divergence. When you talk about divergence, it doesn't matter. Okay? You have to add all x, y, and z.
And what about I?
I is separate because you see,
Okay.
I is well defined. You cannot disturb I.
But here you don't write I. It's a V vector.
I've written the whole equation in vector form. Here, the vector v means vi.
So yeah, okay, this.
Okay, it's vector form. So this is divergence. This, okay, so little bit messed up, but these two terms I have written in form of divergence. And this term is anyways a divergence. So I write all three terms in form of a divergence. Minus V dot sigma. It's minus plus minus. Because there's minus here. Anyway, the question is, sigma is a tensor, but I represent it as a vector here. However, pressure is a tensor, but why we always write pressure as a gradient? Means pressure is a scalar. Gradient is almost defined for a scalar. Whenever I write basically pressure is a tensor, sigma is a tensor. But why I always write pressure as a scalar while sigma as a vector?
We saw in the momentum flux tensor that pressure was only on the diagonal. So it was like V times I. It's like the identity matrix for the identity matrix.
Yes, that's right.
So does that mean we can treat it as scalar? It acts like an adena.
In other words, pressure is isotropic.
Is that what that means?
Same in all directions. So it loses its, technically its tensor. But because our inherent assumption is that pressure is isotropic, it does not change in different directions. So we treat it like a scalar.
So isotropic tensor is just 0 on everything except the diagonals, and the diagonals are the same number?
Yes,
Okay.
that's isotropic. But then what about sigma?
No, sigma is ugly. It can have all the values of flow.
It's basically shear.
Yeah.
Flow in one direction and changing in another direction. So sigma in general is far from isotropic. This is why we can treat it as well. Okay?
Wait, if we're in incompressible, then the diagonal has to be 0 because the c term goes away. So this is only has off diagonal elements.
No, if it's incompressible, then in the definition of sigma,
Yeah, but you have the eta term and the xi term, right?
yes.
So the eta term, you have the entire delta thing in order to cancel out the diagonal elements,
Yes.
and the xi term goes away, so it has no diagonal elements.
But it has other terms.
Yeah, of the diagonal.
Yeah.
Sure.
This is why it is general.
Okay.
That's the answer.
Okay.
Diagonal terms are 0 for incompressible fluids, but because all diagonal terms are not 0, we cannot treat it as a scalar. Fine. Pressure is also 0. I can give this question in the test also. So remember, everything is not in the notes. Whatever we are discussing, sometimes discussion comes, it will come in the exam. I will try to write it in notes tomorrow before, but if I forget, it's better to keep on writing on note rather than laptop. You will miss many things. Many things, even when I teach, I learn here. While you ask some question, and then I learn it instantly as well. So it's not just you, I'm also learning it. But I don't have notebook to write like that, so you should always keep a pen and a book. This is standard way of writing. When you're writing in LaTeX, in laptop, you miss many things. Okay, but that's my opinion, I'm not imposing on you. So where are we? This equation. So this is divergence, but we are not done yet. Okay? There are more terms. What is the last term? Last term is get into V.
Is it divergence?
Minus sigma I here. Now let's look at this equation. We have studied, this is rate of change of energy, and we defined it like this. E kinetic this were like, we can call it EK dot, rate of change of kinetic energy. Or if you want to understand this in better form, let's integrate it over volume. Then we'll discuss its meaning. Left hand side. This whole term here, take 0. The middle term can be, let's call this Q. Okay. This is just flux, energy flux in viscous fluid. You see sigma is here as well. Energy flux in viscous fluids inherently have sigma term inside, but then you have separate term. So this can be converted into surface integral. This is same. Minus. This is sigma prime, not sigma, okay? Wherever I wrote sigma, I'm write sigma prime. Sigma contains P. Sigma prime is only shear term. Now consider that the volume which we are considering is infinite, it's big. It's far from the point we are looking at the layers. In that case, as you integrate, this is F, surface integral. In that case, this integral goes to 0 because the surface integral is infinite, so basically the volume keeps on increasing. So you can consider this term to be 0. In the assumption of infinite volume situation. In that case, the left hand side, which was simply rate of change of energy, kinetic energy, is minus this is what we discussed in the beginning. If you push a viscous fluid, give it some kinetic energy, with time, within a given volume, its kinetic energy decreases because of sigma I.
It says this quantity is always positive for the minus and to turn it negative.
This term is always positive if eta is always positive. Mathematically, it can be negative as well. Physically, it cannot be. If it is positive, suppose, okay, it's a good question. Suppose this is positive. Because we defined sigma prime. So, when now this question came, I thought about it the first time. We defined sigma, it has eta and some velocity gradient terms, velocity derivatives of velocities. Suppose we define it in certain manner that this term is positive. Right hand side is, oh, what does that mean?
Oh, is it the same?
Huh?
Is it the thing with the switching the indices, switch the sign?
No, this is a different question. Whatever you asked is different. It means, what if this term is positive in the right hand side?
What about?
It can be positive if eta is negative, which is okay. In any way, if this term is positive, what it means? First, can it be positive? If it is positive,
Energy is created.
yeah. This is a dissipation of energy. So if you push a fluid from here, if this term is positive, if eta is greater than 0, then your fluid will keep on gaining energy out of nothing, which is unphysical.
No, but our assumption of removing the q dot df was that there's a large volume. That's the surface integral part that we're deleting. And if you say that we're looking at subdividing this area, then it's not small anymore. We can't ignore it anymore.
Locally it is created. This rate of change of volume, even in entire infinite volume, the energy cannot be positive. It cannot increase. The moment you consider it is positive, it is increasing. This is why you always assume that you have to consider theta has to be positive. This is a question of next assignment. My watch is 5 minutes faster. Okay. You don't get Euler equation in exam. You don't get the sheet with Euler equations in exam. Okay.
Okay.
Identities.
But identities is fine. I will give you a page with vector identities.
אחרי
But
שהקננו.
אוקיי.
but not Euler equation.
No, just identities.
Alright. I'll try to remember.
What about us making our own page? Us making our own page with derivation, summaries, things we think we need to remember. Some
Maybe you write everything.
in one A4 page.
I give. Never trust the students. I was a student once.
Look, we had courses. We have a course last semester. It's called the Memphis Spring. It's about partial differential equations. It's one of the most intensive courses in the second year. And last year they allowed open material completely, and they just everyone brought like books of every single exam solved. And then he said, no, I don't allow this. So he reduced it to 2 A4 pages. And even then, it was really, really compressed. We had like stuff up. We had just like subjects with titles, but it wasn't like it was things you need to remember, but it was things that are.
Okay. So there are two types of exams. Either it is open book or no book. I take open book exams as well. Maybe we can take one test like that, with 2 tests. Anyway, I haven't planned yet. But if it is open book, then questions turn out to be very complicated.
Yeah.
Books don't help.
Yeah.
So when I took open book test when I was teaching, students told me, okay, don't take open book. It's better to give it normal.
Yeah, the scariest exams are the ones you have 5 hours, 2 questions, open book, bring all the things you want,
Run in the library.
take it home for the night. Yeah.
That is not applicable anymore. Take it home. That is not applicable because ChatGPT will solve questions for you. That is gone. That's not an option anymore.
We had one course with that last semester. We had a course with the take home.
I will not take that. But I can
It
take.
was a course, he gave to take the test home. I work 2 nights until 6 a.m.
It was.
Can we change the date of the exam? We have a quantum mechanics a day earlier.
Exam, it is not in my hands.
We can.
No, I think you can ask to change it. Other courses we had.
But then somebody else will have some other problem. How will I?
No, but we are most of us in the second year. We
צריך
all
צריך
do
80% צריך 80% בשביל לשנות את זה. צריך לדבר אנחנו עם המזכירות.
כן, אבל היה לנו קורסים שנגיד המתרגלת שלך סקר ואמרה מה שזה אני אשב.
אבל זה הבוחן, לא מבחן.
אוקיי, so it's us.
Yeah, so I don't know how the system works. The exam date is fixed by them.
יש תאריך למבחן?
כן, אבל כן.
Some people who are going in some.
יש פשוט פעם
How
דבר
will the exam look? Will it be more like the first homework you gave, or more?
like derivations,
No,
English
first homework,
answers.
it will be everything: the conceptual questions, derivations, and unit ones. Three sections.
How many questions total?
I don't know when I'll make it. Okay, everybody has come. Okay, let's start. By the way, do you all have books? Did you buy books?
No.
Which book you are following? She has books. Then did you buy books when you have books? How do you study?
With your lecture notes.
No. I'm not that perfect. I will write just notes. You have to follow books. Without books, you cannot study. You cannot understand things. Lecture notes are, I keep it elaborative as much as possible, but books are very much descriptive, so you have to follow standard books. You get the books in library?
We can get them.
Get it. Otherwise, buy it.
I just look at a PDF online. You can just find.
That's also fine. It's up to you. Okay, but you should have books. You can download the books if you want. The book should be, this Lambda Lipstick should be online available from the library as well. Just check it. But you do not read everything from the notes. Notes are not perfect. There can be mistakes, even they are concise. There is no alternative of books, so buy books. Okay. At least one book, which is Lambda Lipstick, that mostly I'm following, if not more. Let's take some examples.
Example of what?
Examples of viscous flows. Okay. So we start with a simple example. Now we derived equations, but what do we do with the equations? We solve the problem. The simplest problem is, suppose there is x, y, z coordinate. Problem number 1. X, Y, Z. So these are two plates, okay? And there's a fluid between the plates. One of the plates is moving with speed u. What will happen to the fluid? That's the question. Now it's a viscous fluid. Because the plate moves, it drags the lower layer along with it, and we want to see from the equations we derived how this fluid behaves. Problem is the same. Constant velocity u. Yes, okay. Now we write the equation that we derived, and it's an incompressible fluid. For simplicity. So we have just one term that defines viscosity. What was the equation that you derived? Let's write it first. This was the equation. Okay. One term which incorporates viscosity. Now if you look at this equation, find out. From the problem we know that the velocity has a gradient only along y-axis. That's what we understood. Because of the plate moves, because of the motion of the plate, the shear is only between the layers at different y. Okay. And there is no pressure gradient. Fluid is pretty simple. It's just fluid is not moving. Only the plate is moving. If there is a pressure gradient, fluid can also move. Fluid is not moving. Only the plate is moving. It is similar to when you put that ball in glycerine's column. The ball moves. The glycerine does not. It drags the layers along the top. So the fluid is moving. So basically, there is no pressure gradient along y. There is no pressure gradient along y. Now, dp dy is 0. Fluid is static. So this term is anyway 0. Simplest problem. We are dealing with the simplest problem. There is no velocities in the fluid in the beginning along y. Along y there are no velocities. But along x, because the fluid starts moving, because of the layer, the lower plate, it will have velocity along x, but there is no velocity along y. So dp dy is 0, which means del square v. What is this for y? It's just, what is del square v? Okay, all coordinates. Along y, it is only okay. Now v is only in x along x, which is also induced by the motion of the plate. So the second derivative of v is 0. How did we find it? From our equations of motion. There is no velocity gradient along y. There is no pressure gradient along y. So the second derivative has to be 0 because these two terms are 0. So this we knew from the equations. But we know v cannot be constant along y. Can it be?
No.
So there is only one component. So dv let's call it constant k. Okay. So there is a gradient of v. V is vx along y because of viscosity. From the equations we find they can be only first order. Second order is 0.
But you need the velocity at the bottom, the y component of velocity at the bottom to be 0, and the y component of velocity at the top to be 0 because of the two plates. So you have a linear fit and 2 points that are 0.
No. The top plate is not moving.
It's not moving.
No.
None of them are moving in y direction.
No. In x direction it is moving.
So, yeah.
So velocity is strictly a component of
Yeah. Okay.
velocity of the plate and the fluid. So the bottommost layer will propagate with the plate with the speed of the plate itself. The plate will drag it along with that. But the uppermost layer, it will not move because the upper plate is not moving. So if speed here is 0, speed here is u, there is a gradient. And the second order is anyway 0.
Oh, it's dou vx of dou y. I thought it meant
V is
dou
vx.
vy.
V is
Okay.
always vx. There is no vy. Vy is 0. There is nothing that can force it along y. You have to be careful. It's gradient along y. component is x. This is what we call shear.
Yeah.
Okay.
Okay.
Solve it. V equals Ky plus C bar. Yes.
What does it change anything if I pull the lower plate very fast? Like when there is a glass on a tablecloth and I push the tablecloth fast, the movement of the glass depends whether I pull it slowly or fast.
Okay.
So how does it come? I mean, how does it change?
Okay, it's a very interesting question. Suppose you pull the lower blade with infinite speed.
Yeah.
Very fast. There is a time scale up to which the layers interact with the fluid, with the plate. Let's call this time scale tau. Okay? This time scale for everything. When I talk about interaction, this interaction time scale. So, depending upon the mean motion of the speed of the molecules, they strike with the lower layer and then come up. If the layer is moving slower, they have time to interact with that. Okay? So there are two time scales. One is interaction time scale, other one is the dynamic time scale of the layer. If your dynamic time scale is similar to the interaction time scale, everything will work whatever we are saying. Suppose your dynamic time scale is infinitely fast, okay, very fast, and fluid is pretty slow, then the molecules will not have time to interact with the layer. In that case, and the layer will not cause anything. That's ideal case. Even if no matter how fast you pull it, there will be some interaction. So it all depends on how fast you pull. If it's very fast, it will be exactly like same. If you pull a page below this can, the can will not even move. It just why? Because you pulled it so fast that it did not have a time to interact with the solid lower surface. There was no friction. Same thing can apply in fluids also. It's little more complicated because fluids are always, particles are always moving. It's not completely static like that. So you have to pull very fast.
So how can I derive it from this equation?
You cannot derive it. You just have to say the time scale is so fast there is no interaction. So there is no gradient. There is no viscosity. Viscosity is not induced. Okay? Now if you put this can solid and you put a liquid, and pull the lower plate with same speed, which will be affected more?
Which of what?
If you pull very fast, let's say some faster speed.
Oh, on the same speed of the same time scale of the it will.
It will affect the water more.
Yeah.
Because its particles are moving, layers are propagating. Fluid is a dynamic system, so you have to pull it very fast so that it doesn't affect. Mostly true. The question doesn't stop here. There's bigger question in that. Because of pulling very fast, second order effects come into picture. Okay?
You cannot neglect them.
If it's very second order effects are that we will study in the next section of the course, for turbulence. It can also cause turbulence. If its speed between the fluid and the lower layer is greater than a certain limit, we will derive the limit. If it's greater than a certain limit, the lower layer becomes turbulent and it's not linear anymore. Okay? That we will study. That's what I mean. Just to complete the answer, I have to make this step out. Otherwise, argument is same. Alright. So we solve this equation. Now remember, V is always Vx. Should I write Vx so you remember? It's not V, it's Vx. Okay? Because there is no component of velocity. It's the simplest fluid, viscous fluid that we can imagine. Okay? Now once you solve this differential equation, you understood this? K dy. Integrate it. V is equal to Ky plus C. You know this, right? Yeah. Okay. Now once you solve a differential equation, what do? You put boundary conditions.
Yeah.
What are the boundary conditions here?
V at y equals 0 is 0. V at y equals height of the contraption is 0.
Y equal to 0, V equal to 0. No,
Y equal to u.
V equals U. Okay, the lower layer is pulling the fluid along with that. Let's see which layer is moving in my box. in the knots, I consider that upper layer is moving. Okay, so let's go along with the knots. Okay. So lower layer is not moving. So V is 0 as at y equals 0, and the height of the plates, the distance between the plate is h. At y equals h, v equals u. So put this here, 0 at 0. So this gives C1 equals to 0. No, it doesn't. Put the other condition. V equals U at H. Good. Yeah, you have to put both the conditions. So C1 was anyway coming out to 0 here. Okay. So U is equal to KH. So this means here, so C1 was 0 and K turned out to be U by H. So V equals
Are we assuming a steady state solution?
no. Yes.
So we delete everything that's Dovila dot E in the main equation.
Yes.
Okay.
There is no time dependence. In this term, there is no U dependence, so Y dependence.
I mean, when you multiply, when you get the gradient of Vx and Vz, they disappear because Vx and Z are 0. So only Vy remains. And then when you have V dot, it's like Vx dot and Vz dot, they also disappear.
Yes.
So
Because
you just have this equals Vy dot Vila dot Y.
yes. So in that case, these terms are 0 in the particular simplest case.
Yeah.
Because these denote the motion along the same direction.
Okay.
The gradient. There is no gradient along x.
Okay.
So V turns out to be Uy over h. U is the speed of the plate.
Wait, why does the Laplacian equal 0 again? The second derivative.
Second derivative is 0.
What's the reason again?
These two terms are 0. When you solve it along y, solve this equation for y. First term is anyway 0.
Yeah.
Okay. There is no motion along y.
Yeah.
Vy is 0. Okay.
The V dot Y does is oh Vy.
Vy is 0. There is no divergence. The gradient. This is completely 0. Okay. Then grad p, del p del y, 0 because there is no pressure gradient. So these all terms are 0. This gives del square v is 0. So there is no second order effect. Considering that our equations work. But the first order is not 0 because of viscosity, then we solve this. Now what does this equation say? It's the simplest way of solving this. This says that velocity decreases with height. Is it?
Decreases.
Increases.
No, decreases. At the bottom it's slow. At the bottom it's high velocity. At the top it's low velocity.
At the bottom it's 0.
At the bottom it's U.
It's U.
No, we change it to the top plane.
Variable is here. H is constant. I'm also getting blackout. Okay. I'm not used to teach 3 hours. I used to have 1 hour class. Okay. So as y increases, velocity linearly increases. So if you plot this, it will turn out to be V H. Okay. This is UV. This This linear increment in velocity is because of the viscosity.
We are only talking about the plate, not about the fluid inside. The fluid it doesn't move.
It does.
Only it does.
Why it moves? Because when the plate starts moving,
Drugs.
it drags the nearest layer of the fluid along with that.
Like the ball in the tube.
Yes. So
Only
ball-
the fluid around the ball is moving with it.
fluid around the ball is moving because the ball is, it's not static system. The ball is falling, it falls down. But here we have assumed that once you start moving the plate, you keep on moving for a long time. Suppose a train is coming. It's like train. A train at the station, and there is a station. Station is not moving, train is the other plate. Okay? Train is coming very long time. So it drags the air along with that. So the layer which is attached to the train is moving with the speed of the train. And that layer pulls other layers as well.
So
So in long time, after a long time, all the layers will start moving. Only the layer which is connected to the station's wall will not move.
so the top platform doesn't move at all. The top
Top
fluid
plate.
in the under
Top fluid.
in y equals 0 doesn't move.
This is upper plate. This
Okay.
is lower plate. Okay. Now it's 2D.
Yeah.
So this moves with the speed u. Then the speed is slower, slower, smaller, smaller. This does not move. Okay.
And this viscous fluid, so it doesn't spill.
Spill.
It,
Spill where?
like it will not disconnect from the top from the top.
Disconnect means what? Where will it go? This after disconnect.
We took it out 2 layers, right?
2 plates.
The fluid is it's layered.
There are many layers. Fluid is fluid. Okay. It has infinite layers.
Okay.
Okay. There are no layers, and we are just imagining many layers. We just put small intervals. It's continuous fluid. But the uppermost portion is dragged by the plate itself. It moves with the same speed with the plate, like a train. Train is taking the air with it. Because it is taking the nearest layer along with that, other layers also start moving because there is momentum transfer. So you see a gradient. U is V is U here, V is 0 here. So you get the solution like this. V is 0 here, it's U here. Okay. Alright. Now let's make the problem a little bit complicated. We'll make it more complicated. Second case. Now assume there is a pressure gradient, which is plates are stationary. Assume the plates are now stationary. Okay, plates are not moving, but the fluid is moving by pressure gradient. Okay, so now we have this force. This is not 0. Now it's conventional fluid is moving, but there are 2 plates. If I write it like that, in that case, there is no motion along x, sorry, there is no motion along y. The fluid is still not moving in y direction. It's moving in x direction. Now the fluid is moving here because of dp dx. We give some pressure gradient. Because of the motion, this term is anyway 0 because it's not moving along y. Pressure gradient is there along x. So this term survives. Second order effect is there. Okay. x is dp dx. But there is no pressure gradient along y. Okay, we'll cross that. Now look at this equation. The left hand side is a function of y. The right hand side is a function of x. So if left hand side is a function of y, right hand side is a function of x.
So it has to be equal to constant.
Both are constant. Okay. They are constant. Solve this.
Wait, how did we get a condition on the pressure gradient? I thought the pressure was out of the problem statement.
First problem, there was no pressure gradient.
Yes.
The second problem, we gave pressure gradient.
Yeah, but you said there is a pressure gradient, and now we just showed it has to be a constant. We just showed the W to X, so it is constant.
Because the pressure gradient is along x,
Yeah.
but the viscous term is only along y.
So this forces, this doesn't, it means we aren't allowed to have any sort of pressure except a constant gradient. Like
No.
usually I thought we were.
We have given pressure gradient, which is constant.
Okay.
The fluid is moving under constant pressure gradient,
Ah.
which is defined in the problem itself. Second problem.
Yeah, no, but I just didn't get.
But when you have this term here,
Okay.
it has three terms.
Yes.
Del square v del x square, y square, z square. There is no z, there is no x, because,
Yeah, there's no motion. Yeah.
but along y it is there. So this is how we got the condition that left hand side is y, and right hand side is x. Okay, so we integrated now. Okay. I can write a DP, okay, it's total definition. See what?
Wait, but C have to be a function, maybe have to be a function of x.
What? What has to be a function of what?
What is the last term?
Here?
No, the last term plus.
This?
No,
This
no,
last
no.
term.
When you solve the integral.
Integral, constant of integration.
Uh,
A. This constant of integration.
But you integrated over y.
Yes.
Uh,
So this dp dx is constant. This whole term is constant. So we integrate a constant with y, constant with dy, it is y. What is the confusion?
never mind.
It's okay?
Yeah.
Integrate again. Boundary conditions. What are the boundary conditions in this problem.
Velocity is to be 0 here and there.
Both the layers, right? Now train is not moving. Train is standing. Station is also static. But the wind is blowing because of pressure gradient. And the train, the speed has to be 0. At the station, the speed has to be 0. In between it increases, right? So we can picture how it will look like. It will look like this. Speed is 0, 0. Okay? This is how it should look like. Put the boundary conditions. At y equals 0, v equals 0. So 0, 0, 0. So b is equal to 0. This is one condition. Second condition, at y equals h, again v equals 0, 0. Okay. So ah is equal to, and a is equal to 1 expose. This is not H, this is eta. Okay. I can take up y as well. Let's keep it like this. Okay. So how it behaves? Velocity. Y equals to 0, velocity 0, y equals h, velocity 0. Plot it, it will turn out to be like this. Now we are seeing it mathematically how viscous fluids behave. What is the average speed?
Cos this
Average speed.
you could do it by integrating cos this parabola over y. So it's just integrate v.
This is average speed, okay? Let's call it V average. Okay? So in both the cases, we obtained V. This I will give an assignment. Just an exercise. Put this V here, integrate and obtain V bar. Can do that? Okay? How the average speed turns out to be. If you cannot do it, let me know. But you should be able to do it. Okay. Now, how the shear stress looks like, sigma. What was sigma? It was sigma ik, right? It was eta. This term is 0. Why this term is 0? It's incompressible. This is divergence. Should never forget that. I will give one example, one question of this divergence in the exam. If that question is wrong, your all marks are 0. Then other questions will not be checked. First, that question will be checked. You should always remember simple things. So this term is anyway 0. What about these terms? Many terms, but our problem is very simple. V has only one component, Vx, okay? And changes the bottom, the derivative is only along y. So you will survive with only one term, approximately. Given viscosity, this is how the shear stress will be given. But then where it is defined, it has to be defined at y equals to 0. Because viscosity is affected at the lower layer, then it propagates. Okay, we are done with this. Last. We cross the time? We are a little bit outside. Okay. Same incompressible fluids, but now it is propagating in the pipe. Now we are becoming more realistic. The fluid does not flow between plates like that, but it flows in pipe. Imagine this pipe.
Square pipe?
Pipe is like this. Huh?
Pipe with given what?
Cross section.
Cross
Some
section.
area.
Okay.
Okay. Now in that case, what will change? Look at the equation.
What is the problem? I mean, what?
The fluid is flowing. There's given pressure gradient. Following from the second problem, there's a pressure gradient along x.
So should we
dp dx is non-zero. We are not sure if it is constant or not. We'll find out. But what about? I'm mostly interested in this term. This term is anyway 0. No motion along y. So we are dealing with these two terms. So let's given pressure, because now it is not one dimensional, right? The plate was at certain y. Now it is over all the directions.
shouldn't we have to work in polar coordinates then?
We will transfer,
Okay.
but because we are in Cartesian, so we can look at the problem like that. We have to work in cylindrical coordinates, not spherical. No, I made a mistake. Can you spot that?
What about
It's not y, it's z. This is because this term is in the pipe surface is in y and z. The motion is in along x. Okay, there is no surface along x. Understood? Previously we had this term only along the plate y.
Y is up there.
Pipe is like this. Okay, this is x-axis. The shear is only along y and z. This cross section is along y and z.
Okay.
Previously it was two plates only along y. So you had only one term. Now we have two terms. Now again you see the same thing. Left hand side is a function of y and z. Right hand side is a function of x. Both are constants. It's constant. But it's a problem in the problem is cylindrical. It has cylindrical symmetry, axis symmetry. So we work in cylindrical coordinates. So cylindrical coordinates, let's start it like this. This is cylindrical R. Cylindrical radius from the axis. You have studied the coordinate systems? Everybody might have. Cartesian, cylindrical, spherical.
yes?
So this Laplacian can be written in cylindrical coordinates like this. This is basically the same thing.
You need it
Hmm?
1 over 8.
Yes. Now, what is gradient of pressures? Pressure changing along x. So typically, let's assume this tube had total length L. Okay. Then I can write grade P as change of pressure divided by L, negative. Just for simplicity, you will understand this. Get rid of this. If you define it like that, we will solve it. Because now it's a cylindrical coordinate now. So minus delta P okay. Now we have to solve this. Multiply this equation with R. Integrate it what? Integrate it over R.
Because we want to talk.
Integrate it over R, it becomes.
What are we trying to find again? We're trying to find the pressure gradient?
We are trying to find V. How velocity behaves in this cylindrical
We're trying to
system.
extract it.
Our purpose was simple. Previously, we found out that velocity behaves like this, and we know it intuitively how it will behave in the pipe.
Sort of zero at the edges and then fast.
Same thing, but in 3D now.
It'll probably be a sine wave. Because,
Sine wave.
like this instead of parabola.
But it cannot be signed there. Sign where is the?
Okay, sine 1.
Let me look at this.
Maybe
Huh?
Gaussian.
No. It's kind of parabolic, but we'll see it. Okay, so let's solve this. Minus delta V over eta L. You should write this because this I will give an assignment. Again, multiply with R. Integrate again. R.
It's 1 over R, not? It's the R square should be R. No.
Yeah, divided by R, right? I'm having brain fat. So this is R. Now we divide it with R. So this will be.
So why it's
This
R?
will be R.
Yeah.
And this will be A over R.
And it's 2, not 3.
Huh? Ah.
R divided by 2. R
Oh.
divided.
This is okay.
No, yeah.
The right side. It
Should
should be.
that? R divided by 2.
Okay. Yeah, still here. Same time. Now we integrate again. This is not grade P, I'm making plenty of errors. Spot my errors. This is delta. We have defined delta. R square by 4 plus A log R. Okay? 1 by R
Plus
B. Okay. Now boundary conditions.
B equal R.
Now the boundary conditions are complicated. Where are the boundaries?
Around
R equals R.
the cylinder. R equal
Around the
R.
cylinder. Let's say the cylinder's radius was, let's say, capital R. Okay?
Sure.
So there are two boundary conditions, but there are two constants, right? A and B. To solve this problem, we need two boundary conditions. One is at the boundary.
What about
One is pretty simple.
center
If
axis?
R equals to R, V equals to 0.
And in the middle, R equals 0 is V equals U.
In the middle,
In the R equals 0, V equals U.
some maximum speed. Okay.
Why is it specifically U? Why can't it be a different value?
What is U?
U is defined using.
By definition, U is the speed.
Oh,
If the fluid was ideal,
yeah.
whatever speed you have given to it because the pressure gradient, this is U. But now because of viscosity, it is changed. Now if it is ideal fluid, it will remain to be U along cylindrical coordinate R, along X it can change because of pressure gradient. So U is the maximum speed, okay? Put it. But, so, huh?
This won't help because you don't know you.
u is maximum speed. Let's say you know it. Some maximum speed u0. Okay, right. You are right. It will not help because you don't know u, but still it will help. So look at this term, the log term. At r equal to 0, it's not defined, right? Okay. So for this equation to be physically valid, this log term has to be 0. This is coming from, you don't know u, but you know one thing about u. U is finite. Okay? If you put r equals 0, let's say, put r equals 0, this term goes to 0. Okay. First, let's put second condition. It's physically very intuitive. Let's put second condition first. At r equals r, v equals 0. So I'm putting this condition. Okay.